Yeah, welcome to our session, the EuroCC webinar, where SambaNova presents themselves. And my name is Martin Mueller. I will be, well, a mini moderator of this session. So I work in SambaNova in customer engineering. And with me is Jennifer Glore. She is vice president at SambaNova running customer engineering. And we will also have an external guest from Chicago, from the Oregon National Lab, who will talk about scientific use cases of our platform. So, Jennifer, stage is yours.
Thank you, Martin, and welcome to folks in the room and folks who are joining us virtually. Thank you. So today we're going to do a brief introduction on SambaNova systems, what we have been working on as far as a product, and then Martin will do a deeper dive into that. So those of you who want a bit more of an understanding can get that. And as Martin said, we'll have Oregon National Laboratory here. They've been a customer of SambaNova's for over 3 years. They started with our first generation product, recently upgraded to our next generation product, the DataScale SN30, and they'll share some of their experiences with our platform and what they're doing in the science space. So first of all, I'm not sure that all of you know about SambaNova systems. So let me just do a very quick and brief introduction. Sorry, we have folks still joining in the room. Thank you for joining. So SambaNova Systems is a company based in Silicon Valley near Stanford University. We became a company in 2017, and our focus is on building an integrated end-to-end solution for the next wave of AI applications. And so we have a combined software and hardware solution that's optimized end-to-end to be the best platform for people.
Weiter erklären, weiter testen und so eben mehr Beweise für die Erwünschtheit sammeln und finden. Was ja auch.
One second, we just heard some background noise that we're trying to correct here.
So I think you can carry on.
Okay, yeah. It looks like whoever was muted. Thank you. Okay, so yeah, back to what we do. We're an end-to-end solution for both hardware and software, optimized for performance, efficiency, and delivering capabilities that you wouldn't necessarily see in more traditional architectures. And so our architecture is one of data flow, which was built specifically for artificial intelligence. And we'll talk to you about the details of what that architecture enables, why we have advantages over traditional computing platforms like CPUs or GPUs, and the sorts of advantages that you get from using our platform. As far as a product perspective, we actually provide 2 solutions, and what solution customers choose really depends on how they want to use the product. Both of them leverage a lot of the same hardware and software that we built, because that's fundamental to what we're doing. And so, as I mentioned, we have developed our own hardware. So that's our own chip, which we call a reconfigurable data flow unit. We package that into systems that we ship as a platform called DataScale. We have a software stack that is a compiler and runtime for AI workloads. And that really fundamentally is our DataScale platform. I'd like to call that as our model-centric solution. So this is really for people who are developing their own models. They may leverage some pre-trained models that we provide, of course, but in the end, they're doing research, or they believe that their IP is in the model. And so they're developing, running, performance optimizing these models over time. When you look at someone like Oregon National Laboratory, this is the product that they have, because they're using models to advance their scientific research. For other customers who don't want to be developing their own models, or are standardizing on open source models for their workloads, or want to accelerate their AI by using these sorts of open source models, we do package our solutions as a service. We call this platform SambaNova Suite. It includes all of the things that come in DataScale, but it's wrapped up to have specific models and service functionality that customers can then leverage. So much of what we'll talk about today is DataScale, because that typically is what applies more to the HPC community. The other thing I'll mention is we just made a very interesting announcement here at ISE just a few hours ago. One of our other customers, Lawrence Livermore National Laboratory, they're part of the Department of Energy complex, has just recently scaled up their SambaNova deployment. So like Argonne, they were a customer that had deployed our first generation products, Datascale S10, and they've now expanded and scaled up that platform to the Datascale SM30. And so we're working with them on our platform to showcase unique workflows that apply to them and capabilities of our platform. To date, just so you guys are aware, we are the largest deployment from an AI accelerator vendor within the Department of Energy. And we also have very large scale deployments at other research institutions around the world. RECON is another example for folks, and that information is available on our website. And with that, I will turn it over to Martin, who will just give you a little bit of a deep dive into our architecture that will hopefully explain where our capabilities and efficiencies lie. And then we'll get on to actual use cases a customer is seeing on the platform.
Okay. Thanks, Jennifer. All right, so I'm Martin, as said in the beginning. So I'm customer engineer, mainly focused around the platform. I'm working out of Germany, and I'm doing that now for 3 decades. I'm doing technical pre-sales. Of course, not for AI accelerators because it's a new field. All right, I give you a quick rundown on our architecture and talk a little bit about the speeds and feeds of our current platform. So what's the big difference, or what's the big thing about our platform? By the way, RDU is reconfigurable data flow unit, and this is the chip we have designed, and this chip lives in the system. And how does that differentiate from normal AI accelerators? So this is a simplified diagram of how a simple graph, like this example up here, is a convolution graph, which by chance is an image example. And the way that is processed on GPU-like architecture, which are all of the competing AI accelerator architectures, is that you program your way through the different layers of the graph. So the graph basically represents the neural network or the AI model. And what happens is if you work through the layers, so you program the first convolution into your thousands of cores. And once you are done processing a sample within this one layer, then you have to store the intermediate results somewhere and load the new context, so the new programming context on the very many cores. So you have a kind of context switching operation in between, and you have to store intermediate results and of course the weights and the data of the sample that you are right now processing, they have to be stored somewhere. This happens on blazingly fast memory, but not much. It's, well, 80 gigabytes. If NVIDIA loves you, you get 80 gigabytes. That is, sounds a lot, but in practice it isn't. So this is basically, these are the simplified ways of how these architectures work. And if you think, well, I would like to maybe fuse these two layers because do a convolution and a pool at one step, which is possible, but then you enter the realm of CUDA programming. So you have to code it yourself. So you create a new artificial layer. And this is basically how all these architectures work. And we call that kernel by kernel programming, and kernels being these various layers you have. And the two challenges you have is memory bandwidth and memory footprint, and host overhead by orchestrating this one. So enter our reconfigurable data flow unit. So the big difference that our architecture has is our architecture is made up of two flavors of, I call them things. I hesitate to call them cores because they are much simpler than a core, but we have very many of them. They are all connected through a programmable mesh of switches. And what we then do is, with our software layer, is we analyze that graph. So first we find it in the code, analyze it, and then instantiate the various layers on the chip. So we do not, by design, do not face two challenges the other architectures have. First, there is no context switching because it's everything there. It sits there. And second, there is by design no need to do something like CUDA programming because these things already sit all next to each other on chip. And when you then, for example, run through a training loop, is you've got external memory, and I'll talk to that a little bit later, is then your batch will simply flow through the chip, and while it flows through, it does the actual processing, which had to be done in other architectures by flipping the contexts. This memory here is DDR memory, which is not that slow, but it's much slower than the 80 gigabytes of memory that GPUs have. But it is only used to store intermediate results. And the one sample you run your training right now on. And this is right now 1 terabyte per chip. So per chip, we have, what's 1 terabyte to 80 gigabytes, a lot more, let's say 20 times more. So we have a much larger memory footprint, which is used only for storing intermediate results and the data sample. The weights themselves are stored in one of the things I have on my switch. If you overflow the weights, yes, you could also store them here, but predominantly they are always stored on chip. And for smaller models, you would even be able to store everything on chip. This is one example that we have, for example, with the work at Livermore, where we have very low latency, small models that are in low latency context, they fit completely on chip. To give you an idea on the hierarchy of bandwidth, you have a bisectional bandwidth on chip, which is in the hundreds of terabytes per second. Well, it's on chip, this is always fast. And then you have 100, give or take 130 gigabytes per second bandwidth to this memory that is off chip. So this, and the important point I want to drive home here is, with our architecture, you instantiate the whole graph. So it sits there and can then be used, either just for inference, or you use it for training. So how does this mapping work? So this is based on work that Kunle Lokuton has done at Stanford, who's one of our founders. And they analyzed, so what are the more, let's say, atomic pieces that make up the graphs that appear in artificial intelligence. And he came up with some time ago already, with this parallel pattern approach or description, which describes a set of unique operations which can represent any graph you see in artificial intelligence. And these are the 5 most important ones. These are not all. There are a few more. But the way you should look at them is, for example, simple is map. It takes a vector of a very high dimensionality and maps it to another vector of the same dimensionality. Every element is mapped to another element. If you're familiar with Python programming, this is basically what you do when you do NumPy vectors. So you have a vector of 1 million dimensions and you do exponentiation. So you do exponentiation about every vector. Similarly, this whole line works like zip. You have 2 vectors creating 1 vector. Reduce is basically reduce a whole vector into 1 value. The most famous example is summing, or doing. If you, for example, combine this and this, you end up with a scalar product, scalar multiplication. This is how you should look at them. And our software stack now takes code, like, for example, a softmax. And I will walk you quickly through how a softmax operation that is quite common in the final layers of AI networks when you do the actual classification, how that is mapped onto our chip. Of course, still very simplified. And first step here is how a softmax would look like if you represent it in parallel patterns. So you've got basically 1 input vector. This is the value, the vector of values you want to do the softmax calculation from. So you do per element map. You arrive at this intermediate result, and then you want to calculate the divisor. So you reduce, create the sum, and then do the zip operation, divide everything by the sum of the values, and this is how you arrive at the algorithm. Another example, and since we share the slides, this is how a layer model would look like. We'll not walk through that. It's the same idea, it just takes longer to explain. So, and how does it happen? So, if you see these two flavors here, one is called PMU and one is called PCU. It's programmable memory unit and programmable compute unit. Important is the memory and compute. One unit, with the empty memory thing, this is responsible for filling values into variables. So doing the actual memory access. The other one, the compute thing, is a simple SIMD unit that can do calculations. If you want to get some intuition how these are to be looked at, is imagine a loop in Python. The Python iterator would run on a PMU. The iterator, it has a little math like iterating a loop variable, so finding out when the loop comes to an end, but it mostly fills values into variables. And then you have the body of the loop where you do actual calculations. This would happen on the computer part, PCU. Here I have my reduction from the previous slide. And now if you look at the mapping, what happens is I take my X values end up here. Then our framework sets up the data path to do the exponentiation in a PCU that lies next to it. One thing I'm hiding here is it also finds out how many of these I need. So if I have a very large vector, it might not be able to do it on just one of these. Then it would add more. So basically, because at the same time, you could take a switching path that leads to another PCU. So this is how this, in the previous image I had of the different size areas, how these are mapped to the actual units. And it distributes, it assigns to all these intermediate results certain areas where they are stored. And then it programs the compute units. And then the data would flow through that whole path. And we are right now also socializing an API where you can basically create your own compute paths to, on a lower level, create your own graph elements. Right now, this is something that our software stack does. So let's now talk. This was basically the principle that we use and which make up all of our systems. So current architecture, SN30s, like we've just deployed an extension at Livermore with the SN30s. It's a rack-based solution, which means rack optimized means it is something that comes in a rack. We ship it in our own rack predominantly. We can move it in other racks, but just work. It's a 10 rack unit large tall thing. It has 8 of the chips I was described in the previous slides. And per node, which is this 10 rack unit thing, we've got 8 terabytes of RAM. It has a SambaNova software stack, which runs on an x86 server, which orchestrates the whole thing. And when you work with the system, you actually log into this x86 server, or you use a job scheduler that uses this x86 server. So although you think it feels like a Linux system, it isn't. We talk to our software stack that runs on this thing. And what the software stack does is, this is an example of the forward direction if you have Python code that implements a model. So what our software stack does, it searches for the forward, extracts that graph, and then maps that graph on chip. We call that process derogatively compiling, which is a little bit, it's more than compiling, but it's basically the command is compiled. What then happens is it takes a forward, it does this mapping. It also takes into account the size of input and output vectors, because this controls how large these areas need to be. Like if I have 1 million dimensions, I need more resources if I only have 10. Obviously. It by default also creates not only the forward path, which is model inputs. And this is kind of nothing if you imagine the normal training loop in Python, where you have first do the model inputs, the forward direction. You calculate the loss. Once you train, you can do it also off chip. Common loss functions are implemented on chip because it's just faster. And the software stack also create the backward path. This is by intention drawn much larger because the backward path, since it contains all the gradients, is much larger. And it also creates a small graph that basically takes the corrections that are calculated here and applies them to the forward direction. So one training step happens completely on chip. Then you would push batch after batch through that loop. And through that process, you would improve the weights inside your model. I see chat. Is that a question?
No, there's no chat. I'm watching it.
Okay.
Or will we share?
Will you share the slides? Of course, I will share the slides. Through Martina.
And please feel free to just chat everyone, because I am monitoring chat while Martin is talking.
Yeah. You're welcome. Because if Martin is talking, he doesn't think about anything else. All right. So the chip. The chip itself is often also called cardinal. And SN30 is the iteration we have right now. The chip itself is organized in 8 tiles. And a tile is 1/8 of the chip. And this is the smallest unit that can be used in a hardware partitioning scenario. So you've got on the system, you've got 8 of the chips. Each chip can be split into 8 things or 8 subset. This means you've got up to 64 units that you can use independently of the chip. This would be a scenario that is interesting if you have very small models that fit on 1/8. So you can do massive data parallel training on just one node. Or if you have different models that you want to run in an inference scenario or training scenario, or you have something in between. You have to a larger language model on the subset of your node, and you use the rest for toying around. Basically, educate people on how the platform works. This chip has a flat view of all the 8 terabytes of memory. So if you have a large model, you do not have to care about all this memory management. This happens all in between, and the system is designed as a flat chip memory. It has its own DDR controller, of course, and the chips have a way of using PCI Express to talk to each other, depending on the kind of traffic they have. So this is the SN30. This is a design of SambaNova. And it comes in a systems package. So this, by the way, is a chip package. Well, they all look the same. And the real ones, I lied, the real ones don't have a color print. So it's just, you look at the heat spreader. It has tons of transistors. It has, on chip, it has 640 megabytes of memory on chip. So it already has quite a decent amount for the weights. It does about 700 teraflops in BrainFloat 16, which is the most common data format you have in AI. And it's fabbed at TSMC in a 7-nanometer process. It lives in the data scale SN30 node. Typically, we configure the racks with 2 nodes in one rack. The reason why we end at 2 nodes is typically you have a 20 kilowatt power envelope and cooling envelope per rack space. If you can cool more, you can put more in. As I said, this is a rack compatible form factor. And every node is made up of 4 chassis, which each chassis having 2 sockets and 2 chips of the SN30 type, and 1 x86 host that orchestrates the whole landscape. A lot of switching infrastructure. And if you have a multi-rack setup up here, you've got switches, and these switches connect to each other. And then one of the racks has a kind of gateway or gatekeeper switch that interfaces with the surrounding environment. So It's using 400 gigabit switches, which have 200 gigabit NICs. So we have a 200 gigabit bandwidth between the switch, between the nodes, and between all the components for data traffic. And then it has a backend management network of 1 gig, which also connects. It's designed for complete lights out management. So we can run it completely remotely with terminal service deployed and others. Nice things. So, right. So I have seen the Murali.
He's on.
Are you on? So
Hi, yes.
yes. So if you would take over control, and I will hand the stage to you.
Sure. Let me share my screen real quick.
Control.
All right, can you see my screen?
Yes. I'm trying to get you a little bit louder.
It may make sense to turn off the camera and move it over there so they can hear it.
Yep.
Yeah, so can you see my screen in the presentation mode, and can you hear me well?
You hear him?
Okay.
Maybe increase the volume a bit.
Oh, the crosstalk, yeah. Okay, let's move it down. 1 second, Marley.
Sure.
But we are hearing from the TV.
Yes, no, from the laptop.
We
We see
saw
the presenters on Zoom.
We thought it works through the TV, but it didn't.
Yeah.
And I've got a 10-meter HDMI cable.
Oh, yeah. That's,
We'll bring him to you.
All right. Raleigh, you should be close. And you should be good to go.
they need ourselves. Yeah.
Yeah, maybe we should be better.
Okay, then I can get started, right?
Yes.
Okay, thank you. Thanks for confirming. Hello, everyone. My name is Mural Imani. I'm a computer scientist at Argonne Leadership Computing Facility. So today I'll be presenting some of our findings with how we are advancing AI for science using the SambaNova data scale at ALCF. So a quick intro. So we are a US Department of Energy lab located in the suburbs of Chicago. So the Argonne Leadership Computing Facility, so we provide world-class resources, computing resources to advance science. So we run a lot of scientific applications at scale. And we have a team of in-house experts who are working closely with the domain scientists to help port their codes to the new systems or running them up to scale at performance. And all the resources are dedicated to open science. So broadly, we can classify the workloads that we see into 3 pillars. We are coming from simulation, data, and learning. And also in terms of the architecture that we are seeing, so we have the traditional supercomputers with NVIDIA 100 GPUs, and we're also getting the Aurora supercomputer with Intel based GPU. And these architectures are currently designed or currently built to advance some of the key science applications at our end. So what we're seeing is an influx of scientific machine learning applications where the AI component is becoming very critical to run the, say, kind of simulations or building some surrogate models where we are replacing part of the simulations. Or we have the experiments is designed like having the AI as AI-driven experiments So we see there's a significant component of AI being involved in these the science applications. So what we are currently investing is on having the infrastructure to facilitate and accelerate the AI for science workloads. So here's a very high level generic snapshot of what we're doing. So on the left hand side, so we see the experimental facility, that is the advanced photon source. And on the right side, so we have computing facility, which in-houses the traditional supercomputers along with different AI accelerators. And in the lower side, we see the kind of science applications that we are currently looking in. So this is a very interesting scenario of you're coupling the experimental facility with the computing facility, and we're seeing a very diverse set of workloads and accelerators. Towards that trend, so we have established the ALCF AI testbed. So this is an infrastructure for having the next generation machines which are tuned for AI workloads. And we provide this platform to help the domain scientists port over their codes to these systems and get their better performance, and want to see how we can integrate these accelerators when we are designing the future supercomputer. So that's one of the key tasks that we have. And in the AI testbed currently, so we have systems. We have the SambaNova data scale SN30 and other systems that we are seeing here. So here is a picture of the SN30 that's installed in ALCF. So we have the next generation hardware, the SN30. And again, as Jennifer mentioned, we started off with SN10, the first generation. Now we upgraded that to the SN30 system. And the configuration is like we have 4 racks or 8 nodes. We have 64 RDUs. And other key capabilities that we are kind of providing is opening this to a broader community to help advance open science research. So the way that we do is if any a researcher or a domain scientist, they want to use this system, so they can apply to the program called as Director's Discretionary Awards. So currently the SambaNova SN30 system is open for allocation. So all it needs is just filling a form with what's the current code or a model or a data set, those kind of details. And there's a quick turnaround time. So we provide allocation on the system, and that really help for just a broader research community. And also the community engagement. So we have been partnering with the SambaNova team, who have been excellent collaborators with us on community engagement. So we host the regular AI training workshops. And along with that, so we have deep dives into the hardware, software stacks, the best practices. And as a user facility, so we also hold external training sessions like there's the AtBESC, which is a 2-week intensive training program. And we also have the ALCF AI for Science training series, which is primarily catered for students. And so we have been working with the SambaNova team to engage with us in this broader training activities. And also we had a tutorial at Supercomputing last year. So when we were able to help the users to understand like how we can program these systems for their science codes. So now let me quickly go through some of the AI for science applications and maybe give more details. So we see there are a lot of applications coming from different domains. Like there's a cancer drug response prediction, or we're looking at some X-ray diffraction based microscopy based workloads called as BRAG-NN or BRAG-speak detection, and the protein folding application. So the kind of workload that we are seeing are totally different in terms of their characteristics, in their domains, their models, their data sets. And I can go through some of those where we have taken these codes, we have ported onto the SambaNova system, and we have been seeing some great results there. So I'll start with the drug discovery domain. So here the project is CANDLE. So the CANDLE project is for doing the strategies for precision medicine for cancer and looking at the exascale deep learning and simulation enabled protein. So here the project includes a lot of deep learning models which are looking at different scales as the molecular level or a cellular level, and based on the drug response. So for specific application called UNO, so the goal here is to understand what would be the drug response for the tumor cells. They are based on different features of the tumor cells and also the drug descriptors and dosages. So this is looking at a very narrowed focus on what's looking at precision medicine for cancer-based problems. So we've taken this code on the SN30 machine, and here we're kind of measuring how performant, how efficient this model runs. So we measure that in terms of the throughput. So so we want to have a higher throughput that's more desired. So here I'm giving a very summary of the numbers that we are seeing. So we are looking at the throughput comparison in samples per second. So we are currently getting roughly 4.5x better performance than the A100 number. So that's pretty impressive for this problem. So the second use case is called Braganon, which is doing a rapid analysis and real-time image detection from the X-rays and the electron microscopy data. So this domain has a lot of implications in some of the key science workloads that we have. And given the increasing complexity of the detector technologies and the workloads, so we see there is a significant boost in how this model runs efficiently. And if you go with the traditional techniques, so on the right side, we see some pictures, but I'll just quickly go to them. So here we are kind of measuring what's the AI-driven model versus the traditional model for doing the peak detection. So with the AI model that's called Braganon, it has 200x improvement over traditional profiling technique. But one of the key challenge here is that the model training capability is kind of limited by the hardware. And again, with the newer or improved detector technology, so we'll be seeing massive data sets with increased data rates as well. So we ported this model on the system, and we'll kind of give two key metrics when we kind of evaluate its performance. So one is the end-to-end execution time, because that's also really important when we look at the workflow. So the end-to-end time is something which includes a fixed time, which is for the compilation, the data pre-processing stages, along with the model training time. So that's the overall time. And the other metric is obviously the model throughput in samples per second. So we want to see like how these two metrics are evaluated when we are running with the SN system here. So roughly we see the overall end-to-end time is significantly lowered than on A100 GPU. And the throughput we see is also improved by 7x factor, so which is, again, very significant that for this workload in general. So some of the ongoing efforts are, so we have been seeing a great push towards generative AI for science, again, including large language models. So one application is called GenSLM. So this is a LLM-based foundation model, and this is trained with gene sequences. And currently, we are focusing on the SARS-CoV-2 and the E. coli viral data sets that we have. And currently, it runs on the A100 supercomputer on the Polaris that we have, from 25 million to 25 billion parameters. And again, we see, or we expect the model size to be increased, and also with the larger sequence lenses of 32K. So currently, so there's ongoing work. So we have ported this code to the SN30 system. We are seeing some excellent results. currently. And the second application is Cosmic Tagger. So this is a neutrino physics-based application where it's a image segmentation task where we want to classify the input pixels into it's a cosmic particle or a muon or a background. The key challenge here is that the resolution of the data that we see is increasingly becoming larger, and we have built this model with Unit 3D based architecture and with high resolution image data sets, which can also be dense and sparse. We have also ported this code to the SN system, and we have been seeing some significant boost up here. On the apart from the workload side, so if you look at more of infrastructure perspective, so currently we're also working with the team to integrate with the PBS scheduler that will effectively help to ease in how the users can run these jobs or have the better job scheduling mechanisms. Now, again, we also see there's the traditional HPC, which is again a key workload domain that we have. So we're also working with their offerings with the SDKs on how we can run the non-AI and the traditional HPC kernels on the systems. And again, there's some ongoing work towards this front. And again, as I said earlier, so we also want to understand like how we can integrate the accelerators with the future generation of supercomputers. So it can be that we have the accelerators on a single node, or they can be disaggregated with a high network connectivity. So that will really shape like how we want to look forward when we are kind of designing the next generation supercomputers. And whatever current work that we are doing will definitely help drive that work going forward. So here we have some of the recent publications from our group. And again, so this is funded by ALCFAR and the US Department of Energy, and there's a whole group of the team who are actively working on this. And any questions, please feel free to reach out to Venkat or myself. I've listed the contact details here. Having said that, so the SambaNova team have been excellent partners with us. So we have been working closely with them, and they're helping us out with all our the science use cases and helping in the Department of Energy mission to accelerate science. And I conclude here, and thank you so much for your time.
Yep, I am here. I'm taking you back. All right. So, let's get the camera back on. But nevertheless, so this basically concludes our webinar on the introduction to SambaNova systems. And if you have any questions, so Jennifer, myself, we will be happy to help out. And we will share the slides through Martina, SambaNova part and the Argon part right after the presentation. And of course, the recording, and we need to find a way how we share the recording. But I'm sure Martina she's nodding, she has a way to actually share the large files. Are there any questions?
I've been monitoring the chat. I don't think there's any. Oh, yeah. Murali, there was a question about the training that you mentioned in your slide deck, which I said was, arranged by Argon, and I would defer to you about, how public those are and whether, if people can get on those lists.
Yeah, so most of the workshops that we have are open. Anyone can register and sign up for those. So we broadcast these workshop or the training session notices to the mailing list or post them on LinkedIn and also in the ALCF or Argon website. So we'll also be having few sessions in the next few months. So one is the AdPesc, which is happening, I believe, in the next June, July, or there's also an SDL workshop coming soon in October. So yeah, please feel free to look at some of the mailing list, like HPC announce, or maybe follow us on LinkedIn or Twitter, where we post those links. Sure, I'll send those links in the chat. Oh, thanks, Jennifer.
No problem. So I think that's just the basic page to Argonne's leadership compute facility. And from there, you can see the test bed, and you should be able to, look at what they have, how to sign up. There's also documentation there, all that sort of stuff.
Any more questions? Yeah. Yeah.
Yeah, so Marley, the question in the room is on the performance numbers you shared. Was it a single A100 to a single RDU, or what was it? And I know you shared the UNO number as well as the Bragg and N number. So I know the answer, but I'll let you comment.
Yeah. So they're kind of running on the same equivalent comparison for both systems. Yeah.
So in the room, they can't hear you, but essentially,
Oh, okay.
I'll tell in the room. It's an equal compare, right? So if it's one A100, it will be one RDU. If we're scaling up large, it'll be always in.
And I get the weekly version because
The question, yeah, so I guess the question was, is the GPU at 100% utilization?
Yeah, I think the utilization numbers were also high. Not necessarily 100%, but I guess they were quite busy with the workload. So we were kind of monitoring the GPU activity as well, and the GPUs were busy at the time.
Yeah, the GPUs were quite busy. Not 100%, but I don't know if anyone can ever run a workload 100%. But yeah, they felt that the GPUs were quite being used effectively.